9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0, and liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
Curiosity is the largest rover ever sent to Mars. Its purpose is to explore if there was once the right environmental conditions to support life. One of Curiosity's instruments is Chemcam, which works as a laser spectroscope that allows the rover to analyze samples from a distance.
Spectroscopy is basically an experimental subject that is concerned with the absorption, emission, and scattering of electromagnetic radiation by atoms or molecules. Spectroscopy is based on quantum mechanics principles such as the wave-particle duality of matter and the photoelectric effect. This subject dates back to 1665 with Newton's famous experiment of the diffraction of light using a triangular glass prism, working with his spare eye as a detector, being able to register only the visible spectrum.
Now we will explain the general setup of a spectrometer. First, we need a gas that is ionized. That means that it has energy that can be acquired by heat or other means. This gas is going to be emitting radiation as photons. The radiation is going to pass through a slit and into a prism that disperses the radiation and through a lens creates spectral lines. Because energy is quantized, this radiation is going to have a unique amount of energy that corresponds to a unique wavelength. So this will create a very unique spectral line pattern for each element. And this way, scientists can characterize samples with unknown compositions by knowing these spectrums that are unique for each element.
Palmer's 1885 fitted model of the hydrogen series shows that the change of orbital of any electron results in a specific lambda, shown by this equation. This equation is also related to a change of energy known as the ionization energy. Later on, it was shown that both of these equations are related also to the atomic number that results in a specific series for any element.
With all this in mind, one of the modern applications of spectroscopy is best exemplified by the Curiosity rover's instrument, Chemcam.
The Chemcam is composed of two very important instruments: the remote microimager, which is in charge of taking images, and the much more important LIBS, which is a laser-induced breakdown spectrometer.
LIBS is a type of atomic emission spectroscopy which focuses a highly energetic laser pulse on a sample by atomizing it and exciting it to form a plasma. In principle, LIBS can detect all elements regardless of its physical state, only limited by the power of the laser as well as the sensitivity of the detector. The laser ablates a very small amount of material in the range of nanograms to picograms, which generates a plasma of up to 30,000 degrees Kelvin, which causes the material to break down into excited ionic and atomic species. During this time, the plasma emits a continuum radiation which does not contain any useful information about the material. When the laser pulse terminates, the plasma starts to cool until it reaches temperatures between 5,000 and 20,000 degrees Kelvin. During this cooling process, the electrons of the atoms and the ions in the excited electronics states fall down into ground states, causing the plasma to emit light with discrete spectral peaks. This way, each element in the periodic table is associated with a unique LIBS spectral peak.
The LIBS has a very powerful laser that focuses its energy in a very small sample, which could be a rock or something else. As we know, the rock is going to absorb a lot of energy until it eventually becomes gasified into a plasma. Because energy is quantized, the gas will be emitting photons of very particular wavelengths, which are then collected by this telescope, which is then going to feed this electromagnetic radiation through a fiber optic into the multiplexer. This instrument is just in charge of separating the ray into three ranges of the spectrum: the ultraviolet, the violet, and the visible near infrared. And it's going to feed these three rays into three spectrometers, which work exactly the same, just with different ranges of wavelengths. So I'm going to explain just one. This arrangement is called the Sesri-Turner spectrometer arrangement. And the incoming rays first collide with a collimating mirror, which is in charge of taking a divergent ray into a parallel ray. Then the rays go into the diffraction grating. This grating has small groups that are going to separate and diffract light into different wavelengths. This diffraction is ruled by the diffraction equation that goes like this. And as we can see, each lambda, which is a wavelength, corresponds to a very particular diffraction angle. So the diffraction grating is going to diffract this ray into very different angles. So as we can see, every wavelength is going to collide into a different part of this second mirror, which is in charge of taking these rays and pushing them into the CCD, which is a sensor that has a lot of pixels. And as we can see, each ray, which is each lambda, which is each wavelength, is going to go into each pixel of the CCD. And that is then measured and taken to a data processing unit.
The calibration of the lips is a very delicate and important step for analyzing samples. The spectral diagrams produced by the processing unit are run through a large database of calibrated known spectral diagrams. The calibrated diagrams were produced in laboratories with approximately 70 calibration standards, including a wide range of igneous rocks, pure minerals, sulfate compounds, and sedimentary materials, all of which are abundant on the Martian surface. The calibrated diagrams allow a quantitative comparison between the experimental results and the theoretical values.
The sensors used in the spectrometers are CCDs, or charge-coupled devices. These sensors are composed of three main layers. The first one is the layer of pixels, which is composed of different electrodes. The second one is a layer of insulator, which is composed of silicon dioxide. And the third one is a layer of semiconductor, which is usually made of pure silicon. When light is incident into the sensor, if this light has enough energy, then by following the principle stated by Albert Einstein in the photoelectric effect, it will produce photoelectrons in the semiconductor layer. Because the electrodes have a potential difference in the first layer, charge will be stored below the electrode that has a positive potential. When trying to read this sensor, a potential difference is swapped between the electrodes. And this way, charge is transferred to the next pixel until charge gets to a computer where the signal can be analyzed. The movement of these charge packets is explained by the principle stated by Heisenberg when he solved the multibody problem in 1930. This principle states that electrons in a semiconductor layer will produce electron-hole pairs. This way, the electron can be transferred into the hole and moved linearly through the array. The electron that is moving through this array simplifies the problem because it can be visualized as a positive particle, or also called a quasi-particle. This quasi-particle simplifies the problem because it does not consider all the interactions between the photoelectron and the other electrons in the solid layer or the other nuclei. Furthermore, since charge is stored below each electrode, then the amount of charge is proportional to the light that is incident into the sensor. And this way the sensor can work as a sensor or detector for the light that is being transmitted into the spectrometer. This way, each photoelectron corresponds to a specific array of pixels, which also correspond to a specific range of wavelength that is being incident into the sensor.
Spectroscopy techniques have been improved over the years, with remarkable examples of the application of modern physics in space exploration, such as the Chemcam experiment. Based on the use of laser-induced breakdown spectroscopy, this system is able to identify elements found in unknown compositions in Martian soil, allowing us to better understand the composition of other planets beyond Earth.